Okay, up till now we've learned how to name epoxides and how to make epoxides, and now we're going to spend some time looking at what are called ring opening reactions of epoxides. And epoxides are in fact very useful synthetic intermediates, and it's because of their significant ring strain, right? That three-membered ring isn't very big with that oxygen, and so it's very susceptible to being opened by strong or weak nucleophiles. And some of those nucleophiles include things like Grignard reagents. So if we think about a Grignard reagent, we have some kind of R magnesium bromide. So the R group has a negative charge, and so that makes a good nucleophile. A hydride, so a hydride is a good nucleophile. An alcohol is a weak nucleophile, but it can be a nucleophile, and we'll look at when an alcohol can ring open an epoxide. And also alkoxides. Alkoxides are strong nucleophiles. Right? They have a negative charge, and so we're going to look at different examples of all of these nucleophiles opening up epoxides. And let's get to it right away. If we have a strong nucleophile, like a hydroxide from, let's say, sodium hydroxide, so here is showing we have our hydroxide doing a nucleophilic attack right here, so we have a nucleophilic attack, and it's going to pop the ring open. So this is the ring opening right here, right? The curved arrow starts on the bond between the carbon and the oxygen, and the pair of electrons ends up on the oxygen to form an alkoxide like this, okay? And so you can see that we're adding that hydroxyl, and we have the 1, 2 carbons from the epoxide, and then we're going to do a proton transfer in the last step. Now again here it's reminding us that the opening of the ring is thermodynamically favored due to the relief of ring strain. Now again, the first step of the mechanism is an SN2 process in this ring opening by a nucleophile, and it involves an alkoxide ion functioning as a leaving group. Although we learned way back in chapter 7 that alkoxide ions do not function as leaving groups in an SN2, this exception can be explained by focusing on the substrate, the epoxide. In this case, the substrate is an epoxide that exhibits significant ring strain and is therefore higher in energy than the substrates that we looked at when we first started looking at SN2 reactions. The effects of the high energy substrate are shown here in this energy diagram on this slide. Now the blue curve represents a hypothetical SN2 in which the substrate is an ether, let's say, okay? And the leaving group would be an alkoxide. The energy of activation for that process is going to be really, really large. This is our energy of activation right here. And more importantly, the products are higher in energy than the starting materials. So the equilibrium does not favor the products. In contrast, when the starting substrate is an epoxide, that I have circled in yellow, we follow the red curve. The increased energy of the substrate has two pronounced effects. The first one is that the energy of activation is going to be greatly reduced, allowing the reaction to occur more rapidly. And second, the products are now lower in energy than the starting materials were. So the reaction is thermodynamically favorable. That is, the equilibrium will favor the products over the starting materials. For these reasons, an alkoxide ion can function as a leaving group in the ring opening reactions of epoxides. This slide shows us that epoxides can be opened by many other strong nucleophiles. And so here we have an alkoxide. So this is an alkoxide. And we end up forming an ether at this part, right here. Here we have a cyanide. So this is sodium cyanide. I'll just write down the nucleophile, which is cyanide, Cn-. And then when we have a cyanide in an organic compound like this, it's no longer a polyatomic ion. Now it's called a nitrile, which is a functional group. The next one, we have a sulfhydryl. So if you have SH-, that's called a sulfhydryl. And sulfhydryl is a very good nucleophile. And then we end up forming what's called a thiol. So a thiol is the sulfur analog of an alcohol. The next one, we have the Grignard. So if we have a Grignard, and in that case, we just add an alkyl group. And the last one is a hydride from, let's say, lithium aluminum hydride, LAH, and we end up adding a proton like that. Now it's important that you understand that the opening of an epoxide by a nucleophile is both regioselective and stereoselective. And so we're going to take a look at that right now. First, let's start with regioselectivity of opening an epoxide with a good nucleophile. It says here, the epoxide ring opening is SN2, and so the least hindered carbon is going to be more reactive towards a strong nucleophile. If we take a look at the two carbons here, if we look at this carbon, you can see that this carbon is tertiary. It's attached to 1, 2, 3 carbons. This is a tertiary carbon. And if we take a look at this carbon right here, you can see that this carbon is attached to only one carbon. And so this is primary, it's less hindered, and so our nucleophile is going to attack at that position. We could even get some practice drawing our curved arrows. Our nucleophile is going to attack the least hindered carbon, and it's going to open our epoxide like that. And after our proton transfer, we're going to end up putting this hydrogen here to form an alcohol on this side. Now what about the stereoselectivity of these ring opening reactions with good nucleophiles? It says here, as with any SN2, inversion of configuration is going to be observed. And so we have the two carbons in our epoxide. We have one here and we have one here. Hopefully you can see that the one that's highlighted in green is less sterically hindered, and so that is the one that's going to be attacked by our nucleophile. Now our nucleophile, since our bond to our oxygen is going up, right? This is a wedge, it's pointing up. That means that our nucleophile is going to attack from the bottom face of the molecule, because it's the least hindered face. And so our nucleophile is going to come in from the bottom, and we're going to get our alkoxide leaving like that. And then of course we have our proton transfer, and we end up with this stereocenter undergoing inversion of configuration. Just like that umbrella flip that we saw with any other SN2 reaction way back in chapter 7. And that summarizes the ring opening reactions of epoxides with nucleophiles. So first of all, regioselectivity, we're going to attack the least hindered carbon. And in terms of stereoselectivity, as with any SN2 reaction, we're going to get inversion of configuration. Now we're going to switch gears and we're going to look at a different set of ring opening reactions. And these are what we call acid-catalyzed ring openings. So something completely different than just using a strong nucleophile. So what happens is when we take an epoxide and we put it in acidic conditions, we can also use that to open epoxides with weak nucleophiles. So some examples of acids that we could use are things like HCl, HBr, sulfuric acid as well. And what are some weak nucleophiles that we could use to open up our epoxide? Well, water is a weak nucleophile and alcohols are weak nucleophiles. And so what we're going to do in the first step is that we're going to protonate the oxygen on the epoxide, okay, which renders it an even better leaving group. And what we're going to do is that in the first step we're going to protonate the epoxide, and that's going to render it, the oxygen, a good leaving group. Then the protonated epoxide can be attacked by a nucleophile in an SN2 reaction. Now, as I said, you can use a weak nucleophile like water or an alcohol when you treat the epoxide with acidic conditions. And so we represent those acidic conditions oftentimes with our proton in these square brackets. And what that means is that you have a catalytic amount of the acid. Every year, over 3 million tons of ethylene glycol are produced in the United States using the acid-catalyzed ring opening of ethylene oxide, shown right here. So we take our ethylene oxide, we treat it with a catalytic amount of sulfuric acid, water acts as a nucleophile, and there we have ethylene glycol. I'll just mention as an aside that as a student in organic chemistry too, you should know the common name of oxirane is ethylene oxide. Now let's look at this reaction in even more detail by studying the mechanism. So again, we start with our acid. The first step is going to be a proton transfer to make a protonated epoxide. So we have that here. And now we can use our weak nucleophile, right? Water is not a strong nucleophile, but we've created a better leaving group. And so we get a nucleophilic attack, our SN2, and then the ring opening. And then in the final proton transfer, we end up forming our hydroxyl like this. And this is a mechanism that you should definitely know this mechanism. Now what about the regioselectivity of this reaction? Under acidic conditions, the nucleophile attack is still going to occur at the less substituted carbon if we have a primary and a secondary carbon present. So you can see that in this epoxide right here, I have a primary carbon, I have a secondary carbon. I'm going to protonate the epoxide, and then my nucleophile is going to attack at the least hindered carbon right here, and that's why I have my nucleophile attached to this carbon. But something that's kind of interesting is that if you have a tertiary carbon present, The nucleophile is always going to go for that. It's always going to go for a tertiary if you have a tertiary carbon. And you might be thinking, well, that's really strange because that's by far more hindered than a primary carbon. Why would it attack there? And there's a good rationale for that. It's true that the primary site is less hindered than the tertiary site, but there's a factor that's even more dominant than sterics. That factor is an electronic effect. A protonated epoxide is positively charged, and the positively charged oxygen atom withdraws electron density from the two carbon atoms of the epoxide. Each of the carbon atoms bears a partial positive charge, shown right here. That is, they both have partial carbocationic character. Nonetheless, these two carbon atoms are not equivalent in their ability to support that partial positive charge, right? The tertiary position is going to be significantly better at supporting a partial positive charge. So the tertiary position has significantly more partial carbocationic character than the primary position. The protonated epoxide is therefore more accurately drawn, like as is shown right here. There are two important consequences of this analysis. The first one is that the more substituted carbon is going to be a stronger electrophile and is therefore more susceptible to the nucleophilic attack. And number two, the more substituted carbon has significant carbocationic character, which means that its geometry is described as somewhere between kind of tetrahedral and trigonal planar, allowing nucleophilic attack to occur at that position even though it is tertiary. To summarize, the regiochemical outcome of acid-catalyzed ring opening of an epoxide depends on the nature of that epoxide. If we have primary and secondary carbons on our epoxide, the dominant factor in that case is going to be the steric effect, right? Our weak nucleophile is going to go for the least hindered carbon. Whenever we have a tertiary carbon in our molecule, the dominant factor will be the electronic effect, and it's going to go, the nucleophile is going to attack at the more hindered carbon, the tertiary carbon. What about the stereoselectivity of this reaction? Well, the good news is that under acidic conditions, the inversion of configuration, like in any SN2, is still going to be observed regardless of which carbon of the epoxide is attacked. And so here we have our tertiary carbon highlighted right here. That's where our nucleophile, our weak nucleophile, our alcohol would attack in this case. And when it attacks, it's going to flip that stereocenter. And so we have the epoxide sticking up, right, because we have two wedges here and we have the methyl group pointing down. Well, since we only have the methyl group pointing down and we've got two bonds pointing up, our nucleophile would come in from the bottom face of the molecule, right? Our nucleophile would come in from the bottom face after this gets protonated in the first step, which I'm not drawing here, but it's going to come in from the back side like this. And so this bond is going to go from being a dash to being a wedge. So we end up inverting that stereocenter. Let's try some reactions here. It says for each of the following reactions, predict the product and draw a mechanism for its formation. So here we start with sodium methylthiolate. So if we draw the Lewis structure for that, it would look like this, sodium, right? And then we have our methyl thiolate like that. So we have a good nucleophile, and this is not an acid-catalyzed ring opening. This is just a nucleophilic attack on our ring, and so it's going to attack at the least hindered carbon, and so we're going to have our nucleophilic attack like this. There we go. We have our ring opening like that. If we draw the intermediate that's formed, we're going to have our oxygen, our alkoxide like this. We have our methyl group down here, and then we're going to have our sulfide. So we're going to have our bond to our methyl group to our sulfur like that. That's called a sulfide. And then in the next step, we do our proton transfer. Proton transfer like this. So let's draw that. Here we go. We'll pull off our proton. And then the final product is going to be this. So we've got our alcohol here, our methyl group at our stereocenter. And there we go. There's our sulfide. Let's try the next one. We have lithium aluminum hydride. If we draw out the Lewis structure for lithium aluminum hydride, I'm going to leave out the lithium and just draw the aluminum hydride ion like this. So hydride is going to come in and attack at the least hindered carbon like that. We're going to get our ring opening like this. And let's draw what the intermediate would look like. We've got our methyl group down here. We've got our oxygen up here, our alkoxide, and then we're just adding a hydrogen here, right? So here we already had two hydrogens attached, so basically you're ending up with a methyl group like this. And then after the proton transfer, practice our curved arrows. There we go. We end up forming this compound, which you probably recognize. So if I just draw a bond line structure, right, you can clearly see that this is not a stereocenter, okay? That's not a chiral carbon. And so what you actually end up making is isopropanol in this case. So you just end up with isopropanol. There we go. Okay, let's take a look at the last one. We're attacking with sodium ethoxide. I'll just draw my ethoxide like this. I'm going to attack the least hindered carbon, which is this one right here. Have my ring opening. I'll draw the intermediate that's formed. I'm going to have my alkoxide on this side. And then I'm going to have my phenyl group down here. I'm just going to write pH to abbreviate phenyl. And I'm going to have my ethyl group down here like that. And then on this side I have my O ethyl like that. And then I do the proton transfer like this. Draw my curved arrow for the proton transfer like that. And then we'll draw the final product, which is this right here, like this. I have my phenyl group and my ethyl. There you go. I've gone ahead and evaluated the stereochemistry of the two stereocenters and the products. You can double check me to make sure they're correct. This one here, this is an S configuration, and then this one here is also an S configuration. All right, let's take a look at 13.18. It says for each reaction, predict the product and draw a mechanism for its formation. You can see that both of these are acid-catalyzed ring openings. So the first step is going to be protonation. So I'm going to start out by drawing my hydronium, right? I'm going to have hydronium when I have a mixture of sulfuric acid and water. And so the first step is going to be a proton transfer. And there we go like that. Let's draw the protonated epoxide that we get. There's our proton, there's our positive charge. We'll draw in our methyl group, and we'll put this methyl group over here, and our ethyl group. Now we're going to have our nucleophilic attack. Now which side is our nucleophile, which is water in this case? It's a weak nucleophile, but it's our nucleophile nonetheless. So if I draw my water, is it going to attack, is it going to attack here or here? That's the question. Well, if we evaluate those two carbons, if we look at this one, this is a tertiary carbon, and this one here is a secondary carbon. And remember that when we have a tertiary carbon, that electronic effects are going to dominate because it's going to be more comfortable with the partial carbocationic character, and so the water is going to attack at that carbon, the tertiary carbon. And so let's draw that curved arrow. Now something else I want to address here is the inversion of configuration, right? Because it's going to attack from the bottom face of the molecule like this, and then we're going to, of course, have our ring opening. Now, the inversion of configurations that you're used to seeing in this class are usually when we go from a dash to a wedge or a wedge to a dash. But what's happening here is that you have the methyl and the ethyl group, and you see how they're pointing down? They're pointing down, okay? With respect to this part of the molecule, right, they're both pointing down. But what happens is after our nucleophilic attack occurs, they're going to be pointing up. Let me show you what I mean, and I'll leave that scratch in there for now. So what we're going to end up with is something that looks like this. So we have our hydroxyl like this. We're going to have this methyl pointing down, and now our methyl group and ethyl group, they're not going to switch. It's not going to go from a dash to a wedge and a wedge to a dash. They're going to go from pointing down to pointing up. So now our methyl group is going to be pointing up, and our ethyl group is going to be pointing up like this. And then we have our oxonium like this. And then in the last step, we do a proton transfer. And so another molecule of water is going to come in, and it's going to do the proton transfer like this. And we're going to end up with our final product, which is this. So I have my hydroxyl here, my methyl group, right? My ethyl and my methyl are pointing up now, okay, like this, and I have my alcohol pointing down like this. So again, just to reiterate, the methyl and the ethyl were pointing down, and now they are pointing up, right? If you look at the plane of the molecule, they're on the other side now, and that is the flip, okay, of the stereocenter. That's the inversion of configuration. Let's take a quick look at the last one. We're going to start out with protonation. So we're going to protonate our leaving group. What we're actually going to have as an acid catalyst in solution will be protonated methanol, like this, okay, because we have a mixture of sulfuric acid and methanol. And so we're going to have our protonation in our first step. And I'm going to draw the product up here to make sure I don't run out of space. And there we go. We have our protonated epoxide. We have our methyl group coming down here. The other carbon, this isn't a stereocenter, obviously, because we have this cyclopentyl all attached to the same carbon. Remember, I told you that's called a spiral arrangement. But now we have methanol as our weak nucleophile. And the question we need to ask ourselves is, where is the methanol going to attack? Is it going to attack at the more hindered carbon or the least hindered carbon? Well, let's evaluate those. You can see that this carbon here is tertiary and this carbon here is secondary. And as I told you in the first example, that when we have a tertiary carbon, the electronic effects are going to dominate, and so the nucleophile, the methanol, is going to attack at that carbon. And so we can draw our methanol. Let's draw our methanol like this, and then we're going to have a nucleophilic attack like this, and there we go. And let's draw what the product will look like. So again, we have this ring pointing down, and now it's going to be pointing up in our molecule. And let's draw what that would look like. We have our methyl group, we have our hydroxyl. Now our ring is going to be pointing up like this. That's the best I can do for right now. Then we're going to have our oxonium like this. And there we go. And then in the last step, we're going to have a proton transfer, where another molecule of methanol is going to pick up that proton like this. There we go. And then we're going to draw our final product, which will look like this. Let me draw this spiral ring a little neater this time. There we go. Is that an improvement? Maybe. Like that. And then we have our methyl ether down here like this.